All right. Hi, everybody. Happy Monday. Welcome to tonight's AP Physics 1 CRAM session. This is number 8, and we're going to take a look at rotational motion part 2. So we're going to kind of pick up where we left off last week, do one torque question just as a recap, and then dive into rotational energy and angular momentum. And that's kind of the plan for tonight's stream. All right. Coming up, well, in case you haven't noticed, the exam's a week from Thursday, which is kind of getting close. So what we're doing Wednesday, we'll do basically FRQ practice. Topics, it's all open for anything. So we'll do some Q&A. I'll also pull up some old paragraph response questions and qual-quant questions. And we'll just go through, again, what topics are they talking about? How can we recognize those? And then some tips and tricks for structuring responses, that sort of stuff like that. Then on the 13th, so that'll be next Wednesday, there is a 5-hour mega stream. That 5-hour mega stream is going to be kind of broken up. You guys don't have to stay for the whole thing. You can pop in and pop out as needed. But basically, it's 2.5 hours of student-led review. We've got a couple people on staff that are basically taking the exam. They're experts at it. They're going to lead some reviews about what they think is important. Then we'll break for trivia at about 7. And then at 7 o'clock, I'll come on and we'll do, again, open Q&A, final questions, tips, tricks, anything like that you guys have before the exam starts up. All right, so that's kind of where we're going here, coming down to the wire. Also, just to point out, next Wednesday, we also have the 1 o'clock open Q&A stream. So we'll do open Q&A at 1 o'clock for everybody, not just a CRAM one, and then specifically FRQ practice Wednesday night as well. And I think the same thing for the 13th. Open for everybody at 1 o'clock, and then CRAM session starting at 4. Okay, so skip through this stuff. Plan for today. Rotational motion review. We'll hit the kinetic energy part. We'll hit angular momentum and a bunch of examples. Also check out the community FRQs. This one is paragraph length response. If you do it by Friday, I'll post my comments and stuff like that on there. And also go back. There's 8 more paragraph length response or FRQ type questions. Go ahead, check them out. And then as you post them, I'll go through and leave some feedback and how you can improve and get some more points on the exam. All right. So today's chunk is kind of this table. There's a lot of stuff on here, and really a lot of this stuff is just the math. All these equations are on your reference tables. They don't need to be, most of these equations are on your reference tables. You don't need to memorize them. All we need to do is realize, hey, we're talking about rotational stuff. I'm going to look for these equations on my reference table. Okay, for today especially, we're going to be focusing on a couple of them, especially the momentum one, angular momentum, L equals I omega. We'll hit angular kinetic energy, 1/2 I omega squared. We'll talk about how you have kinetic energy of a rolling object being translational, side-to-side motion, and rotational going on there. We'll do some with angular momentum about changing angular speed. We'll do a little bit with planets and look at orbits and how we can use angular momentum to help us figure out the speed at a given location. And of course, a little bit of conversion between linear and rotational sort of terms. So V equals omega R, S equals theta R, all those useful ones that are super handy to have in the back pocket. By the way, these ones right here in this table, this S equals theta R, V equals omega R, A equals alpha R, are not on your reference table. These are ones that I would strongly recommend jotting down somewhere, even on your reference table when it comes time for the exam, because going from linear motion to rotational, they are essential for that sort of thing. All right, so that being said, we're not going to do this question. We're going to skip ahead here and do, where is it? We're going to do this question. This one is kind of where we left off from last week's. It's a string wrapped around something, falling down, do some stuff with it. So we'll do this one, and then the last part of it we'll use as a transition between linear, or between rotational dynamics and torques and stuff like that into more of doing energy and angular momentum. So that's kind of where we're going. Give me a second to swap over to the right screen, and we'll get started solving this. All right, so hopefully that is there, and it is big, and it is in focus, because that'd be ideal. All right, so we're going to start off with this sort of thing. This is a string wrapped around a hoop. They gave us the radius of the hoop and the mass of the hoop. The string's attached, and we're told the moment of inertia is mr squared. Okay, and now we're supposed to find some stuff. Do a free body diagram, find the acceleration, find the tension, calculate a time, and an angular speed. All right, so let's start off with part A. How many forces are there acting on the hoop? I've got 2 in the chat. Yes, so mg. Now, where does mg act? At the center of mass. Good. mg acts in the center, and that's going to be important for us later on. And then we have tension acting on the left-hand side. So mg, center going down, tension on the side. All right, review from last week. Which one of those 2 forces can exert a torque on the hoop? Tension. Yes. Good. Yes. So again, we need to figure out a torque needs to be a force times a radius that is perpendicular. Gravity does not have a radius. It is acting at the center. So its R is 0, and therefore it is not making a torque in this case. So very good. All right. Cool. Free body diagram. Done. Nice. Check it off. Part B. Find the acceleration of the center of the hoop when it descends and the string unwinds. All right, so acceleration, we're looking at something with forces and masses and stuff like that. So we're going to start with Newton's second law. Okay, now, why am I doing forces? Well, we just had to do free body diagram. That's kind of a good lead into, hey, we're talking about forces and stuff like that. It's not guaranteed, but typically it's a good place to start here. So F equals ma. The hoop is descending, which means which force needs to be bigger? mg. There we go. Cool. So this is mg minus t equals ma. And the reason I do big minus small is it gets the direction of the acceleration right. So acceleration is going to be a positive downward number there. All right, great. The only problem here is I don't know what t is. They gave us values for r and m, so I can find mg, and I'm looking for a, but I don't know what t is. So we've got to go from linear motion to rotational motion and look at the hoop. So for the hoop, sum of all the torques must be I alpha, Newton's second law for rotation. And we already mentioned the only force that's making a torque is the tension. So the torque is going to be T times R. I is mr squared, so let's just write that in there. And then alpha is going to be A over R, using that handy conversion, A equals alpha R, alpha equals A over R. Super useful to have in there. So are we defining clockwise as positive in this case? I'm defining downward acceleration as positive. So whatever that's going to work out to be. I'm not going to get caught up in the semantics of is this clockwise torque or counterclockwise torque. The signs for this and the A are going to be the same. So yeah, we're going to see this thing rotating that way around as a result of it. So it is a clockwise rotation, and that is our direction of torque, direction of angular acceleration, and then our linear acceleration will be downwards in that case. So solving for this, all the r's drop out. So we get rid of this r, the r squared, and that r. So I'm left with t equals ma, which is nice. We take that t, we plug it back in to our forces equation, and I get mg minus ma equals ma. all the m's can disappear. So G will equal to A, or A is about 5 meters per second squared. Okay. It's also perfectly fine to leave that as G over 2 with that. So yeah, there's part B. Questions? Okay. Well then, let's look at part C. Find the tension in the string. Well, the nice part about this one is we already have an equation that is solved for the tension. We have T equals MA. So in this case, super simple. Tension must be equal to MA. All right, so normally, lefty-loosey, righty-tighty, a counterclockwise is a positive torque because that will loosen something, and a clockwise will tighten it. Yeah, yep, Jess, that's right. But again, in for what you're seeing with AP questions in general, at least specifically AP1, they're not going to get into what is it, a positive torque or a negative torque. They're going to get into the effects of it. Is this going to increase your angular rotation? Is it going to decrease your angular rotation? That sort of thing is where we're looking at. So less getting caught up in positive, negative, and more getting caught up in what's the effect of it. So in this case, this torque is going to make it rotate, and that's going to cause it to roll downwards in there. Yeah, you can definitely define directions whatever way you want. You have complete control over positive, negative, and stuff like that for any of these questions. Absolutely. The only thing would be just make it clear which way you're using it. Like in this case, I'm indirectly saying down is positive. It probably doesn't hurt for me to be more explicit in that. But yeah, just make sure you're clear if you're doing something crazy with directions and signage and stuff like that. All right, so and while I'm not expecting a ton of math and stuff like that, there's a C part with numbers. All the math I am expecting is going to be relationships or derivation sort of stuff, not so much with hard numbers. But that's part C. Pretty straightforward. We already did all the work in part B, so it's a nice, easy free point there just to grab and plug in and go. All right, continuing on. Part D, calculate the time it takes to fall 1 meter. All right, so time is a little bit tricky. I wouldn't say, maybe not tricky is not the right word. Time is one of those that we don't have a ton of equations that will help us solve it. But in this case, we have our kinematics equations. And pretty much anytime we're talking about time, it's either going to be period equations, TSP, TP, 2 pi square root of L over M and stuff, or stuff L over G, stuff like that. Or it's going to be X equals X naught plus V naught T dot dot dot, or V squared equals V naught squared plus dot dot dot. In this case, they tell us a distance. So we know a change in Y right there. So I'm going to do something like Y equals Y naught plus V naught YT plus 1/2 AT squared. In this case, we're looking at 1 meter equals 0 plus 0 plus 1/2. We got to make it, no, I can positive 5. T squared. So T will be equal to the square root of 2 over 5, which is a number that I can put in my calculator and get an answer. 2 divided by 5. Root is roughly 0.2828 seconds. So we're dealing, looks like 2 sig figs here, so I'll just leave it as T equals 0.28 seconds for that part. All right, so diving back into a bit of kinematics again, simply because we're talking about time. Normally, we don't see those sort of questions. Normally, it's forces or momentums or stuff like that. But in this case, we're going all the way back to September, October time periods. So all the way back there. All right. We good so far? Yep. Okay, cool. Now, for the last part E, we're going to do this one two ways. Did I totally botched the number completely wrong here? Hey, how about that? Square root of 2 over 5 is 0.632. Not that. We'll just pretend that never happened. 0.63. Yeah, it's what happens when I try to type in Google and don't put parentheses around stuff. So there we go. Square root of 2 divided by 5, maybe? Who knows? Anyway, there it is right there. Good catch, guys. So last part, calculate the angular speed of the hoop after it has traveled 1 meter. So 2 different ways we can do it. We can do it with kinematics. We can do it with energy. So I'm going to start off by doing it with kinematics just because that's kind of the kick I'm on right now. We just did a kinematics question. We've got accelerations, stuff like that. Let's do it with kinematics. Then we'll go back through and do it with energy again, just to show we're going to get the same answer both times. So in this case, I'm looking for a speed. I'm looking for an omega. I, again, have a delta y going on here. I know the acceleration, and I know my initial velocity. So doing something like v squared equals, v squared equals v naught squared plus 2a delta, well, I'll do delta y in this case. What I'm going to do is find the velocity and then use my handy dandy little v equals omega r equation to convert from linear to rotational. Okay, so I'm going to find the linear speed, and that should correspond with the rotational speed in there. So v will be the square root of 0 plus 2 times 5 times 1. Okay, so the square root of 10. And then that means omega must be equal to v times omega is v over r. So that's the square root of 10 over 0.25. Let's do omega equals alpha times time. Yeah, I could. I definitely do an omega equals alpha t. And then alpha is a over r. It's going to be the same sort of thing because we do know the time. That's true. We do know that 0.63 seconds. That works equally well. Yep. So that works perfectly well with that. And there's nothing wrong with that way either. So let's be the square root of 10 divided by 0.25. And I got this to be approximately, and please check my math, 12.6. Well, hold on, 2 sig figs. 12.6. Yeah, we'll call it 12.6, really. So about 13 radians per second in there. So yeah, cool. So it sounds like we agree, which is great. It's always good confirmation. All right, so there is one way to do it. Using kinematics, whether you're doing linear or rotational, either way works. Both ways are perfectly fine there. Let me do it now with energy, just to get us into the feel for where we're going for the rest of the stream. In there, so let me change colors, and we will dive into that part. All right, so for energy, energy, what we can say here is that this falling disk, or this falling hoop, is converting potential energy due to gravity into translational kinetic energy and rotational kinetic energy. That we have potential energy mgh, 1/2 mv squared because it's moving downwards, and 1/2 I omega squared because we're rotating. So let's write that out. I don't want another color. Mg delta y equals 1/2 mv squared plus 1/2 I omega squared. And yeah, let's just sub in here. I'm going to stop clicking that part. Mg delta y equals 1/2 m. I'm going to sub in, this is omega r squared plus I times mr squared omega squared. We're trying to find omega. So we're looking for the angular speed. Again, just showing that you can do it a different way with energy. So I'm trying to find omega out of all this. So that was not the right button. This is the right button. There we go. So just a little more room for me to work here. So it looks like every single term has an m in it. So let's get rid of those. We'll just cross off all the m's. It also looks like I can't really do much else, right? But I've got omegas and r's and stuff like that. So that's all good. Now, normally we do this, we're finding V. So it's a little bit backwards from what we normally do with energy, but it works out perfectly fine. So we're going to have G delta Y, 1/2 omega R squared, 1/2 omega R squared. So this is just omega squared R squared. And then we'll get G divided, or G times Y. So that's 10 over 0.25 squared. Whole thing square rooted is omega, and then that will give us the same 13 radians per second out of it. So either way you do it, whether it's kinematics linear, kinematics rotational, or energy, we end up with the same result every single way. Okay, which is good to know. It doesn't matter which way we choose here. All right, questions on that question? Are we good to move on? Okay, so let's see what else we can find here. Not that one. Momentum, maybe. Ooh, this one, that's a momentum one. Momentum. Okay, let's do some energy ones to continue with this one here. Continuing on the theme, this one, very easy compare sort of question. Definitely something we can see on next Thursday. Compare and then explain your reasoning why. So a paragraph response or something like that on there. So I got 4 objects: a solid sphere, a hollow sphere, and 2 blocks. On there, the spheres roll down the ramp without slipping. The blocks have frictionless ramps. The ramps are identical in cases A and C. The ramps in B and D are also identical to each other, but not as steep. Let's rank the spheres by the speed they have at the bottom and explain why. All right. So I've got an all the same option. I've got B and C are the same, and that's bigger than A, which is bigger than D. I got a couple others too. Okay, interesting. Well, let's talk through this. So all the same could be an answer, right? Let's talk through here. So in both cases, both answers I see in the chat here, they're saying B and C are the same, regardless of the other two. Why would B and C be the same? They have the same delta Y. Okay, so they are talking about the same change in height. What else? Or is that all that matters? Just keep notes up here. So blocks B and C have the same, actually they're all blocks, right? Right, so they have the same mass, the same inertia, sure, yep. Okay. That works, I guess. Yeah, that'll work just fine. All right, so B and C, same mass, same inertia. What's the physics principle we're getting at here? All translational kinetic energy. There we go. Okay, yeah. So we're talking about something about conservation of energy here. Okay, so this is, I'll write out the math in a second here. but all objects try to, the typing game on Fiveable could be really useful here because I'm struggling writing stuff out, and I can imagine if this was actual exam, trying to spell stuff right and write stuff out could be kind of stressful. So all the objects start with the same potential energy, and it gets converted into kinetic energy. So far, so good. Okay, B and C have the same potential energy to gravity and kinetic energy. Change in energy is greater in C. Okay, why would C have a greater change in energy? I mean, isn't energy, if we're just going to write this out here, potential energy, let me done this for a second. So potential energy is just mg delta H, right? And they all have the same mass. They're all 1 kilogram. And they all go down 2 meters. Okay, so they will have all the same changes in potential energy. So steepness doesn't matter, not for energy. The steepness would matter in the time it takes to get down there. But this question doesn't ask about time or acceleration or stuff like that. In this case, they're just talking about when they reach the bottom, what happens. Absolutely, C will get to the bottom faster than B will. But they will end up with the same kinetic energy at the bottom, regardless of when they get there. Okay, yeah, so C will have a greater instantaneous change in energy because it's a steeper ramp, absolutely. Yeah, but we're looking at start to finish. Don't care how you got there. So they will have the same total stuff in there. Okay, so we're just comparing top to bottom because that's what energy is really good for, is beginning and end. Don't care about the middle sort of parts. If we cared about the middle, we do kinematics or forces or something like that there. All right, so far, all the objects start with the same potential energy. It all gets converted into kinetic energy. So they should all be the same, right? No, good. Okay, so what am I oversimplifying here? Yeah, there are 2 kinds of kinetic energy. Okay, and this is something for you guys. As I was looking through practice prompts that I put out and stuff like that, some of you guys are getting a little confused with the idea of kinetic energy, rotational kinetic energy, and translational kinetic energy. When I write out a question, and I have my kids do the same thing, I never just have them put KE. Because KE could be rotational, or it could be translational. And if we're not sure, I don't want to confuse the different things together. Okay? With case B and C, you can do RKE, I do KER or KROT, that sort of thing. That's fine. Or even KE rotational. What I don't want to do is have KE and then KER and then talk about energy and stuff like that. I want to make it very clear to the reader that we're talking about either this is translational kinetic energy or it's rotational. Okay. Just to be super clear on that, because it can get very easy to confuse them. Some of the potential energy. A and C, yep, A and D, good catch. I got it. So far, I'm just building up my case here. Notice I haven't said anything about who wins yet. I'm just trying to build up the logical process. So I get to a therefore at the end here. ERTIA, inertia. The other part I would mention here, this question isn't exactly perfect or going to match up for an AP question. For an AP one, they don't actually tell you the moments of inertia. So they would say this, for example, is I equals 2/5 mr squared. And then for D, I will equal 2/3 mr squared. So they would give you those values in the question too. That this one is more an APC style, where they would have you basically just say, here they are. You should know which ones are which, prove it. But in this case, you guys will be told moments of inertia if you need them in here. But it's greater in case D. This means B and C have the most. And there's my finished explanation there. So does this response work? So another way to write it here, B and C have the same delta Y, and all their gravitational potential energy becomes kinetic energy, so they have the largest final speed. Okay, I would tweak that. All their gravitational potential energy becomes translational kinetic energy, because in all of these cases, gravitational potential energy turns into kinetic energy. The only trick here is we have to worry about which kind of kinetic energy. So I'd be very explicit on, even for B and C, it's translational, no chance of being rotational on there. Okay. A and D have gravitational potential energy, become both, so their final speeds are lower. However, D has a larger I than A, so more energy is required to turn D, which leaves less energy for D. Yeah, that works good, John. That little tweak in there, talking about whenever you're mentioning kinetic energy, be clear as to what kind you're mentioning. But yeah, that's good. Yep. Also, it doesn't hurt to talk about, I mean, you could go through and do the math here and talk about how potential energy turns into these. For B and C, it's V equals square root of 2GH. For A, it'll be, oh goodness, some fraction in there. So inertia and translational kinetic energy are inversely related. So here it is. Kinetic energy rotational is 1/2 I omega squared. So bigger I means more rotational energy. Okay, they're directly related. Our big assumption here, or our big setup, potential energy due to gravity turns into translational and turns into rotational kinetic energy. So if you end up with more kinetic energy or more rotational energy because you have a bigger I, that means the linear one, the translational one, must go down as well. And therefore a smaller velocity at the result. So you can say they're inversely related, assuming you're starting with the same amount of potential energy. A object that is rotating faster will have a slower linear one. Yeah, I guess you could say that. We can even break this down even further. Let's do it for the sphere, so that's a little bit easier. MGH 1/2 mv squared plus 1/2 I omega squared. GH equals 1/2 v squared plus 1/2 of 2/3 v squared. I'm skipping a couple steps in here. I skipped the conversion from omega equals V over R, dropping out all the R's, plugging in the I and stuff like that in there, just to make this a little bit easier. So 1/2 and 1/3 make 6. So GH will equal 3/6 plus 2/6. So that's 5/6. V squared, V will equal 6 GH over 5 square rooted. Is that right? 1/3 is 2/6. Yeah. Yeah, that works. Whereas before, in these cases, V will equal the square root of 2GH. So you're ending up with a smaller fraction and therefore less speed in there. So you could actually do the math out and just say, hey, here's the equation, here's the setup for each of these, and that'd be perfectly fine too. Nowhere in this did it say you have to do only qualitative and not quantitative as well. All right, good to move on? Let's see what else we get. Okay. This one's similar. Do we want to do another similar one or move on to something new? Something new. Okay, everybody wants new. Okay, new. Okay. All then. How about this one? This one's new. Actually, it's an old question, but it's still new. Wait, so D was the slowest? Yeah, so if we go back, Meg, D was the slowest because it had the biggest moment of inertia, so that it would rotate, spend more of its energy in rotating and less of it moving sideways. So it would be the slowest one on there. Yep. Okay, so now new stuff. Fine. So space shuttle astronaut goes in a circular orbit around Earth, has an assembly of 2 small dense spheres, each of mass m, whose centers are connected by a length L and no mass. We also get to shoot something at it. Okay, so mass m, speed v naught, express all your answers and stuff like that. All right, so we're going to shoot this at it. It's going to hit, and it will do stuff, right? We're supposed to find the total kinetic energy after the collision and the change in kinetic energy after the collision. All right. So they keep mentioning the word collision here, which hopefully should ring bells, that somewhere in this collision thing, we should be talking about momentum. So we're doing something with momentum and something with energy in there as well. So let's look at this. So part A, let's start with P before equals P after. Beforehand, we've got one object moving, so that's the clay with this momentum of mv naught. And afterwards, it's going to hit and stick to the center of the rod, so now its mass will be 3m, the mass from the clay plus the 2 m's from the rod, moving at some speed v, so that means v must be equal to v naught over 3. So we're moving slower here. Kinetic energy is 1/2 mv squared. So that's 1/2 of 3m, because I want after, times v naught over 3 squared. All right, so that is 9. 3 drops out there. So this will be m v naught squared over 6. So a little bit of potential energy, or a little bit of momentum to find the velocity, and then kinetic energy from there. For double I, we're looking for the change in kinetic energy. So this will be final minus initial. So we have 1/6 mv naught squared minus the original, which was 1/2 mv naught squared. So let's see. Wait, where'd the 6 come from? Okay, so let me back up a second here. This chunk right in here, you're going to get 1/2 times 3 times 1 over 9. So 3 over 9 gives me 1/3. And then 1/2 times 1/3 is the 1/6. Okay, so it's all the weird, it's all the numbers that aren't the mv naught squared part in there. Okay, so in this case, continuing part 2 here, we've got 1/6 mv naught squared, final kinetic energy, and then this will really be 3/6 mv naught squared. So we're left with a negative 2/6 mv naught squared. Okay, so we lost energy here. Just as a recap, for those of you who didn't pick up on the momentum part here already, what type of collision is this? Elastic or inelastic? Inelastic, yes. Okay, good. Remember those vocab terms. They could come in handy in here, but this is definitely inelastic because our energy change was not 0. All right, cool. Excuse me. All right, continuing on now. We're going to do the same thing, except for this time we're going to aim a little bit differently. Nope, the spheres and the rod, we're here to let you do it part B without changing too much. So here now, part B, we're going to do the same thing, except for now we're going to shoot it at the end of the system. So instead of shooting in the middle, we're shooting at the end. Oh no, how will we do this question? If only we knew rotational stuff and angular things, that could make it a lot easier. What was the answer for AII? I got negative 1/3 mv naught squared. In there. So, yep. Okay. Also, in case you guys don't know, I am going to post a PDF of these at the end of the slides and link it on Fiveable too. So you can go back and check our answers and work and stuff like that too. Okay, so now we're looking for some sort of angular momentum rotating sort of thing going on here. I just need to find the right page in my notes here, so I'm not going to tell you something completely wrong because that'd be bad. All right, so direction of motion, distance from the left end of the rod to the center of mass of the system. Okay, so here's something we don't do a ton in AP1. This is an older question, which is why it's on there. We need to find the center of mass of a system. So for center of mass, we're going to look at it being, grab the right pen, there we go. So for part I, center of mass is basically mr over m. So it's the sum of mass times radius over the sum of masses. You guys may have used this equation in your classes, or this may be brand new. It's not something I expect to show up on AP1 next week. Okay, this is APC. It's an old question. Okay, but at the very least, without using any equation and stuff like that, we should be able to figure out what's on the bottom. It's the sum of all the masses. So it's the sum of the mass times the radius over the sum of the mass. Okay, so we're supposed to figure out from the left end of the rod, stuff like that. Yeah, it is next week. You'll be fine. We got plenty of time, and it'll be good. It'll be good. So in this case, what we're going to do here, we're calling this end 0 meters from that point. So mass times radius, we're going to look at each of these masses after they stick in there, and then talk about their stuff. So in this case, the sum of MRs, I have this mass M. It is 0 meters away from the end I care about. So its radius is 0. At the other end, I have a mass of 2m, and it is a distance L away from my 0 mark. So 2ml, mass times radius, adding up all the individual parts. In the denominator, I have a total mass of 3. So my center of mass will be 2ml, sorry, just 2L, not ml, because that's 3m. 2L over 3 away from that left edge. So realistically, it's going to be somewhere right in that point. Okay? And that's how we find our center of mass. Now, conceptually, we could have said that same thing pretty easily. Oh, it should be closer to the heavier side. Okay, so it's got to be on the right-hand side of the center, closer to the heavier side, and we have a total mass of 3. It's split 1/3 and 2/3, so I should be 2/3 away from it. That sort of thing in there. But that's how you would figure that out. Again, not expecting it to be on the exam, but that's how you would do it on there. I don't think center of mass is on the reference sheet. That's why I'm thinking it's not on there. Let me double check. Yeah, it's one that I know is on the APC reference tables. But again, it's old question. Don't worry about it. This is just simply the math if you felt the urge to do that. Part B, we kind of already did too. Unintentionally, I drew the arrow already. Part B, the direction of the center of mass has to be going upwards. Okay. All the linear momentum before this collision was directed upwards. So the center of mass still needs to be going upwards afterwards. P before equals P after. Linear momentum still applies here on there. Yeah, so as Jeff said, we're looking at doing linear, not linear, just doing the concept. It should be closer to the heavier end of the rod, not the lighter end. And it should not be halfway. It should be maybe a little bit less than halfway. That sort of thing like that. So on there, they may give you a question if they want to do it. And they may have like A, B, C, D on that point and say, okay, what letters is the center of mass closest to? That sort of thing is what you need to know, not how do you calculate it exactly. Okay. Yeah, so going back to part B, center of mass must be going straight up because linear momentum is still conserved. P before equals P after. It was going upwards at the beginning. It's got to be going upwards at the end. Okay, now I'm going to skip ahead a little bit here and do part 4. I'm going to cheat because, again, this is AP1, not APC. So I'm going to tell you that the moment of inertia of this whole wonderful contraption will be 2/3. Yeah. 2/3 ml squared. So I'm going to tell you that just like you would in an AP1 question, they would tell you that. I'm going to tell you the same thing. So the moment of inertia of our object after the collision is 2/3 ml squared. We're supposed to find the angular speed of the thing before and after the collision. All right, this is where angular momentum comes in. Okay, we've done our linear momentum stuff. P before equals P after. That got us the direction. That's what we did in part A. Now we got to do rotational stuff. So this is for part 4. Angular momentum beforehand equals angular momentum afterwards. And here again, I'm going to cheat a little bit. I'm going to use my notes. This is not in the reference tables, but I highly encourage you guys to write this part down. The momentum of the clay before the collision is mv0 r perpendicular. Okay. Angular momentum on your reference tables has it as I omega, which is correct for a rotating object. But it's also equal to mvr for a linear moving object. Okay, this part right here. So linear momentum, P equals mv. Angular momentum, L equals mvr. Just like with all our linear rotational things, if you take the linear term and tack an r on the end of it, it becomes a rotational thing. So V equals omega r, A equals alpha r. So why is there an r now for this guy? Because it is angular momentum, not linear momentum. We're going to find a simplified equation. We don't have any numbers to deal with, so all we can do is find a simplified equation here, or a derivation, or something along those lines. Okay. So what I'm going to say here, L before will equal mvr because that is angular momentum on there. And we'll have to figure out what r is in a second here. Afterwards, we're all rotating, so I'm going to use I omega because we're looking for angular speed. We're looking for omega at the end of this. So keeping I in there, or keeping omega in there is a good idea. All right. So we've got mv0. Now r is our radius from our center of mass. So in this case, if our center of mass we were found out as 2L over 3 to the left-hand side, that means the radius on the right-hand side must be L over 3. And I told you, 2/3 ml squared. And then I'm looking for omega. Okay. Which one, the I value or the R value? L over 3. Okay, so R for rotational things. The R in angular momentum, mv naught R. So angular momentum, mv naught R. This R is the distance from our pivot. Or in this case, it's the center of mass. It's the point we're going to rotate around. So because we have an entire thing that is L, yeah, we got to go with center of mass. So because our entire thing is L, we know our center of mass is 2/3 from the left-hand side. That means it's 1/3 from the right-hand side. So we have to use L over 3 for the radius from the right-hand side. Does the m in 2/3 ml squared refer to the whole system mass or just 1m? It is the whole system mass simplified. So that ml squared is just the m term in there. Okay. Yeah, and so Bree, hopefully that this helps. We're talking about angular momentum, not linear momentum. So linear momentum, P equals mv. Completely agree. I'm not changing it into P equals mvr. I'm talking about L, angular momentum, is the linear momentum P times the distance from the radius. So it's, no, all of this is rotational. I omega is rotational momentum. So the only part about linear stuff here, we have, as we did in the first part, we did P before equals P after. This is our linear stuff, lowercase p. In our chunk here, we have to do rotational because now we're spinning around this point instead of moving in a straight line. So I omega is angular momentum. I know it's confusing because it's a capital L. I don't know why it's a capital L for that symbol, but it is. And that is just the part we have to deal with here is there. So is that a fact or just for this problem? It is a fact for any of those. L will equal MVR. And we can prove it with a different sort of setup, but it is a provable fact in there for any of these questions. Typically, the only time we're going to use it is if you have an object moving in a straight line that suddenly runs into something else and makes it rotate. So in a case like this, we will use L equals MVR. Another example we can get to is planets orbiting. We'll talk about angular momentum being mv radius and stuff like that. In this case, v is the speed we're moving at. So we're told its speed at the beginning is v naught, and r is the distance from the point of rotation. So we are rotating and spinning about this center of mass, which is where that blue arrow sticking out is. So we have 1 on the other side, 1/3 on one side, 2/3 on the other side. And that's where our R is coming from. John, so because which mass though, when it collides. So when I'm doing MVR, it's the one that is colliding. And when I'm doing I omega, it's the one that's spinning around a point. Both of them have angular momentum, which is kind of weird to say that an object moving in a straight line has angular momentum, but it does. So when we talk about MVR, we are talking about something moving in a straight line. And when I use I omega, I'm talking about an object that is spinning. Okay? They're equal to each other because both those are two ways we can write angular momentum. It's just a little bit easier to do MVR for linear moving things and doing I omega for spinning things. Point object mr squared. Yeah. Will this be on the test? I'm not expecting it to be. I would definitely expect maybe compare angular momentum and stuff like that beforehand, or talk about is this conserved. Let me get through this one, and then we'll do I'll jump right over to a planetary one, which may be a little bit more straightforward with that. So yeah, basically this comes through, stuff drops off, and go from there. So drop the m's, drop the L, and we're left with our omega being a number. We drop the thirds too. Omega equals what? 2 V naught L over 2. There you go. So there is our omega after the fact. All right, now angular momentum stuff that could be on there. Let me just revamp this. And another good case for using MVR. Okay, this one could be on there. I think I've done this question like this before, but you've got a planet. Let's call it a planet with mass M, and you've got a little satellite orbiting in an ellipse. So a little m over here, and it is orbiting around in some sort of elliptical path. And they ask you, hey, if I know the speed at this point, so let's call this point A, and I know the speed right here. This is VA. What is the speed over here at this point when you are a radius B away from the planet? Okay. This is also an angular momentum question. And we can do it one of two ways: I's and omegas or MVRs. This is one case where MVRs are your friend. So what you can do is, because there's no outside torques, there's nothing changing the rotational speed of this object other than gravity acting between the object and the planet. So the entire system is closed. There's no outside torques. There's no outside forces. We can apply conservation of angular momentum. L before equals L after, or in this case, L point A equals L point B. So and again, using this L equals MVR part on here, we can say mass velocity at B, radius at B must equal mass velocity at A times radius at A. The mass for one of them was insignificant. So in general, Meg, the mass of the satellite or the object orbiting will pretty much always cancel out, whether it's a circular orbit, or in this case, we're dropping it out because it's the same on both sides in there. So it just falls out in the math that it happens. I'll do a circular orbit question in a second just to prove that again. So in this case, we get the velocity at B is the velocity at A, radius of A over radius of B. Okay. And this is where we get to the part where we could talk about speeds and stuff like that. All right. So yeah, so that was masses drop out in this case. If we were talking about a circular orbit, just because I said I was going to, if we're doing a perfect circle, not this kind of drawing here, little m, we would do something like F equals MA, G big M little m over R squared equals little m V squared over R. The little m's again drop out. One of the R's drops out, and you get V equals the square root of GM over R. So again, little mass disappears in the math. And that's typically what you're going to see for most of these questions. The mass of them are not going to be important. So for a circular orbit, it drops out. For a elliptical orbit, it drops out. In all these cases, whether we're talking about energy, potential, and kinetic, both had the same M's and stuff like that in there. So yeah, there we go. Bree, I have no answer to that one. I have no idea about how they're scoring the Olympics points and stuff like that. I would say you've been on for long enough, I think, but that's a good question. I can reach out and see if I can figure out an answer for that one. But yeah, I have no idea. They just kind of started that. 25 minutes was the answer. There we go. Okay. So that being said, this sort of question, I can see a lot on there showing up. This is angular momentum. This may get talked about where you have more potential energy, less kinetic energy. This is less potential, more kinetic. You could do some period things in there. You can do Kepler's laws with taking this F equals ma part and getting the period equation, your t squared equals 4 pi squared r cubed over gm, sort of thing like that. This is where I would see angular momentum show up a lot. A lot of the other ones will probably be something more along the lines of, if it shows up at all, it's going to be conserved because we had no outside forces or torques. That's my thought. Also, if it puts your mind at ease a bit, it's a 2-question test. I don't see angular momentum being a major component of a 2-question test. Do I see forces, energy, rotation sort of stuff? Yes, but I don't see angular momentum in and of itself. And I may be completely wrong, but I don't see that being a crux to you need to know this one little concept in order to figure it out. I would think you're looking at things like conservation of energy, Newton's laws, something else in there. So if I had to put money on it, I'd say you have a simple harmonic motion question that does energy and forces, and you probably have some sort of momentum into projectile motion question or something like that deals with the other 2 topics. I don't see angular momentum being a huge part of it. But then again, I won't know until you guys do. Actually, I won't know until after you guys do, and I hear from my kids. So I wouldn't stress out entirely about it. I would make sure you know, at least have resources ready for you for that exam. Note sheet, maybe a sample problem or something like that filled out. But this is not something I would lose sleep over if I don't understand every single intricate part of it. I would lose sleep over if I didn't know Newton's laws F equals ma inside and out, if that helps. All right. So yeah, great. Thank you guys. If you want to do me a favor before the next stream, so that'll be before Wednesday, if you guys could shoot me an email, my email address is on there, and just let me know what sort of topics you want to cover. Next time is open Q&A, free response question, tips and tricks. So if there are certain topics or certain questions that you may have seen on another stream or something like that you want to go over, shoot me an email. I'll make sure I put those in there. And then check out the community posts. And other than that, yeah, have a great rest of your day and stuff like that. Okay, a sample problem for every unit for a note sheet. Yeah, I'd probably say that having one worked out question is not a bad idea, especially because you've got open notes and stuff like that. It's not a bad idea at all. And even if you want to look through like the old AP questions that they post, College Board posts, has scoring guidelines and stuff like that there. So, and they have sample responses as well. So you can go through and say, oh, for this particular wording, this is what's going to get me a 4 points out of 7. This wording is going to get me that 7 out of 7, sort of thing like that. So you can go back through and actually check the results and stuff like that there too. Okay, yeah, not a problem at all. So, now let me just answer this question. Comment and paste. I hope that helps. Yeah. All right. Yeah, I would recommend anybody who's going to that get that stuff from College Board. It's nice and simple. It's kind of what I'm stealing from a lot too. But all right, have a great weekend, guys. I will check in on you later. If you have any other questions, I'm going to hang out. I'm just going to close the stream for a little bit here. So you should still be able to chat and stuff like that.